Hello, I welcome you all in this presentation related with the subject fundamentals of surface engineering. We have talked about the various processes which are used to modify the surface characteristics so that the wear resistance friction behavior of the component can be improved, and how those processes can be classified. Apart from that, we will now be looking after the surface characteristics which should be considered or which should be designed in such a way that the required resistance to wear and friction can be achieved. So, in this presentation basically we will be talking about the various properties which are important from the friction and wear point of view. So, there are, although can be various bigger categories like the metallurgical properties, mechanical properties of the surfaces, but if we look into the finer details of those properties, then we will be having these 5 sets of the properties. Five surface properties. One is the surface energy, the second is the chemical composition of the surface and near surface layers, then the microstructure of the surface, hardness of the surface and the surface roughness. These are the general surface properties which affect the way by which loss of material from the functional surfaces under the various surface under the different types of the wear conditions will be taking place, which may be in form of like adhesive wear, abrasive wear, erosive wear, corrosive wear, fretting wear, and likewise there are various types of the wear. So, in general we will try to talk about the way by which these properties of the surfaces affect the wear and friction behavior of the material. So, in this presentation I will try to talk about the first 2 properties, and thereafter we will take up the other 3 characteristics. So, as far as the surface energy is concerned, surface energy which is generally measured using this parameter represented by this gamma, and the joule per meter square is the unit which is used to quantify the surface energy, and surface energy is about the energy required to create unit area of the new surface after breaking the bond. We know that whenever any component when subjected to the external loading, so obviously somewhere the crack will be nucleated. So, whenever one crack nucleates, it creates the 2 surfaces, one surface is this and another surface is this. So, creation of such kind of the surfaces needs energy. So, energy required for creation of surface is known as the surface energy. And how does it happen? Like there is a continuity of the metal or the material, but whenever crack is created, crack is nucleated and it grows, the surfaces, new surfaces, 2 new surfaces will be created, and the amount of energy which is required for creation of such surfaces depends upon the way by which the different constituents of the material are held together, means the kind of the bond, type of the bond which exists. So, the different materials can have the different types of the bonds which we can see here. One is the covalent bond, ionic bond, metallic bond, van der Waal bond, hydrogen and molecular bonds, etc. So, there can be various types of the bonds between the constituents which are making a particular material, and energy required for breaking those bonds also varies, and which in turn governs the surface energy. So, stronger is the bond, greater will be the energy required for creation of the surface, and which in turn will be governing the mechanical as well as wear and friction properties of the material. So, if we see here the way by which surface energies of the material are different types of the materials which are which will be having different types of the bonds, like the covalent bond needs the maximum has the higher surface energy, like 1000 to 3000 megajoule per meter square. This is much higher than, means the covalent bonds need they have much higher, they offer much higher surface energy as compared to the materials having the ionic bond and the molecular bond. So, now if we see a material which is having the ionic bond, and if it is subjected to the application of the external force during the service, then the material having the covalent bond, which requires much higher surface energy for creation of the new surface, then it will require greater energy for breaking of the bonds and then subsequently creation of the new surface. So, surface energy of the material varies with the type of bond, and different bonds offer the different types of the surface energy. So, accordingly the efforts required for creation of the new surfaces will be varying, and this in turn will be affecting the mechanical and wear friction behavior of the material. So, now if we will see surface energy, we know that now surface energy of the material decreases with the increase of temperature, and this happens due to the increase in amplitude of the vibrating atoms. Further, the methods are there to alter the surface energy. There is one very famous classical Griffith theory on fracture, which says that the surface energy directly affects the, which actually relates the discontinuities and surface energy with the stresses required for the growth of the crack if it is existing in a material. So, the size of the crack and surface energy, these two are used, and according to this, higher is the surface energy, greater will be the stress required for the fracture. So, the fracture stress increases with the increase of the surface energy. Because it directly governs the energy required for creation of surface, and which in turn is influenced by the kind of bond which exists between the metals. So, actually there are different approaches. The surface energy of the material can be altered, like in one typical example, if this is a component and if you want to break this. So, what we will be doing, we will apply certain kind of the chemicals at the surface. So, surface energy is reduced, and that will help in creation of the new surface using the lower level of the energies or lower level of the stresses. There is one typical example where ice blocks are broken using some kind of compound at the surface, so that the surface energy of the ice is surface of the ice is reduced, and then ice can be broken using much lower amount of the impact force required for the fracture of the ice block. Means by changing the composition or surface impurities of the material, it is possible to alter the surface energy, and which in turn will be affecting the way by which surface will be behaving under the influence of the external stresses. So, absorption of energy at the surface of the material can decrease the surface energy appreciably, and which can be used to regulate the surface behavior as per the requirement, whether it is for fracturing we have to reduce the surface energy, and for increasing the strength we can increase the surface energy. There are various types of the surface energies, and surface energy is measured with regard to particular kind of the environment, like this solid is in contact with the liquid. So, surface energy of the solid liquid interface will be expressed like the gamma SL, which will indicate the solid liquid interface surface energy of the solid liquid interface. And similarly, if this is a solid and in contact with the gases like air, then it will be solid vapor interface. So, one solid, so that is this one, the solid surface in contact with the gases. So, there will be solid vapor interface surface energy, and the liquid in contact with the gases surrounding the molten metal. So, the interfacial energy in that case will be termed as the gamma LV, or which is the liquid vapor interface energy. Like solid interfaces, like in the matrix, there are certain particles. So, there will be interface between the two matrix, and in the second phase particle there will be interface between the two. So, the kind of interfacial energy which exists between the solid and solid, that will be governing the resistance to the crack nucleation at the interface. So, the mechanical resistance will be affected accordingly. So, surface energy of material is measured with respect to the surrounding environment, forming an interface at the surface, and accordingly we will see that the solid surfaces or the solid vapor interfaces will be behaving in the different ways. Say the surface energy of the solid interface determines the fracture resistance, as I have just said that this is the solid and having the solid second phase particles. So, there will be solid interface, and energy between them, energy at this interface will be determining how much resistance it will offer for creation of the crack and then its subsequent growth. So, the fracture resistance is influenced by the surface energy of solid interfaces. Surface energy of the liquid vapor interface influences the friction and wear behavior, especially under the conditions under the lubricated wear or the sliding conditions. While under the dry sliding conditions, where the two metallic surfaces are interacting with each other under the dry conditions, and in that case the solid vapor interface surface energy will be important, and low surface energy of an object with the solid vapor interface results in the less wear, and which is good for the good wear resistance. According to the Rabinovich, very famous tribologist, he had in his book he suggested that the surface energy and the surface energy at the solid vapor interface are directly proportional to the friction coefficient and the wear respectively. So, surface energy, higher the surface energy, higher will be the friction coefficient, and higher is the surface solid vapor interface energy, greater will be the, so greater is the this solid vapor interface energy, greater will be the wear loss of the material. So, it is preferred that from the friction and wear point of view, it is preferred that the surface energy and the solid vapor interface energy is low. There is another form of energy which is very commonly used, is the stacking fault energy, which is found directly proportional to the stacking fault energy is found. So, SFE, stacking fault energy, is found directly proportional to the wear loss. So, higher is the stacking fault energy, greater will be the wear loss of material, and inversely proportional to the work hardening behavior. So, if we see this trend, so if we see this one, if the material is having higher stacking fault energy, then due to the surface layer deformation under the wear conditions, there will be the faster removal of the material from the surfaces, and that is why the wear loss will be high. On the other hand, when the stacking fault energy is low, then material tends to harden rapidly. It's the inverse relationship. Higher the stacking fault energy, lower will be the work hardening characteristics. So materials will not be hardening much despite of the surface layer deformation. So the loss of the material will be faster, while in case when the surface stacking fault energy is low, material surface layers will be work hardened rapidly, and so they will be resisting the abrasion and the surface layer deformation quickly, and which in turn will be resisting the loss of material from the functional surfaces. So, stacking fault energy is one of the important parameter. It is always preferred to have the low stacking fault energy, so that the material loss in form of wear is less and the work hardening tendency of the material is high. So, this is what I have just explained. The low stacking fault energy causes low stacking fault energy under the during the deformation, under the deformation conditions. A material having the low stacking fault energy under the deformation conditions will form the more twins on the plastically deformed surface, and these twins interferes with the slip movement, which in turn will be resisting the deformation, and resistance to the deformation of the surface layers under the wear conditions, especially when there is a metal to metal wear, or under the abrasion conditions also. So, when the material is having low stacking fault energy, it results in the more twins on the deformation, and increased number of the and these twins will be resulting in increased interfering effect on the slip of the material, having the more twins, especially in case of the low stacking fault energy materials, and that in turn resists the deformation. So, for greater work hardening effect, and if the material surface layers are being work hardened, or they are having the greater work hardening effect, then it will be leading to the reduction in wear, and which in turn will improve the wear resistance. So, what is preferred, that if the material is say mild steel, then we would like to have the surface layers designed in such a way, engineered in such a way, that it has the material of the low stacking fault energy at the surface, so that it work hardens rapidly under the wear conditions, especially under the adhesive wear conditions, under the cavitation conditions, and solid particle erosion conditions. So, because in all these cases some kind of the near surface layer deformation will be experienced by the material, and if it is having, if the surface layers are having the low stacking fault energy, then these will be work hardened very rapidly, and which in turn will be reducing the resistance, will be reducing the deformation, and reduction in deformation of the surface layers in turn will be increasing the resistance to wear. So, if you have to understand in another way, surface energy is the energy with the surface to remain in the equilibrium. All the materials will have the different constituents of the different sizes and different shapes. The energies are associated with each of these, such as the grain boundaries which are present in the material, twin boundaries which are present in material, energies associated with the locked in strain, which happens due to the differential change in volume, especially under the non-uniform volumetric change or non-uniform plastic deformation, or thermal cyclic heating, or the metallurgical transformation. So, all these will be leading to some kind of the locked in strain. So, these locked in strain energies associated with the grain boundaries and the twin boundaries. So, some kind of energies are associated with the material, and to have some kind of equilibrium with these energies, surface energy is required. So, surface energy is the energy with the surface to remain in equilibrium with the surrounding. Now another important characteristic of the surfaces that will be affecting the wear and friction behavior of the material is the composition. So if we see all these properties like surface energy, chemical composition, hardness of the material, microstructure and surface roughness, except the last one, all these first four properties are somehow interrelated. So that is what we will be talking, like we have talked about the surface energy, and it is required that surface energy low to have the good resistance to the wear and friction. Higher surface energy results in the larger wear particles, which in turn results in the higher wear rate, as well as the high surface energy also causes the greater friction. But the surface energy of the material is also found to be sensitive of the chemical composition and the microstructure. Similarly, the hardness of the material is also found to be dependent on the chemical composition and the microstructure of the material. So somehow all these characteristics are interrelated, and which will have the impact on the wear and the friction behavior of the material. So since the chemical composition is of any material which is made of a particular composition, say if it is simple carbon steel having 0.2% carbon, in that case it will mostly have say 80% of the ferrite and 20% of the perlite. This will be having particular, for each composition there is the particular set of the phases which will be there under the normal conditions. If you want to change the surface properties of such kind of the material, then by altering the chemical composition of the surfaces, we can have some another set of the microstructure present at the surface. We can have another set of the mechanical properties, another set of the microstructure, and another level of the surface energy. So alteration of the chemical composition affects all these characteristics, and that's why chemical composition of the surface predominantly determines the wear and friction behavior, because it directly affects the surface energy, surface microstructure and the surface hardness. Since these three characteristics are being influenced due to the change in chemical composition of the surfaces, so it is important that surface, if it is possible to regulate the surface characteristics, surface chemical composition, then it will be regulated in such a way that we are having suitable combination of these surface properties like the surface energy, microstructure and hardness of the material surface. So the change in chemical composition, according to this one, since the chemical composition affects the surface energy, microstructure and hardness, which is one type of the mechanical property, so it is good to change the compositions if possible, so that we have required combination of the microstructure. Change in microstructure, as I have said, it can change the different types of phases which are present and its grain structure. So change in grain structure and phase structure is possible, and which can lead to the variation in the matrix phase, which can lead to the formation of the various types of precipitates and various types of the compounds. So for example, if this is the surface of simple 0.2% carbon steel, which had like say at the surface 80% ferrite and 20% of the perlite. So we can change this by changing the surface composition, say introducing the carbon at the surface. So this increased carbon content will be increasing the perlite under the normal condition, but if the controlled heat treatment is carried out, it can lead to the production of the martensite at the surface layer. Similarly, we can introduce nitrogen also. So introduction of the nitrogen at the surface will be leading to the formation of the iron nitride. So it will offer us the different set of the properties which were not actually present at the surface of the simple mild steel or low carbon steel having 0.2% carbon steel. So it can be any other material. So like we can take simple aluminum silicon alloy, and its surface can be modified in such a way that it has a desired composition, so that it results in the desired set of the mechanical properties, the microstructure and the surface energy to offer the required wear and friction behavior. So change in microstructure can lead to the variation in these aspects, like phases can change, grain structure can change, and as far as micro constituents which are present, there can be variation in the matrix, there can be variation in the precipitates and the intermetallic compounds which are being formed due to the change in chemical composition. So what can be done and how the change in chemical composition can affect? One aspect is that it will change the phases, it will change the constituents which are present at the surface. Apart from these change in phases and the constituents which are present, it can lead to the grain refinement. Means we can add just at the surface layer those constituents which will help to refine the grain structure of the surface layers, so the properties are enhanced. It can lead to the formation of the solid solution, like addition of the alloying elements can form the solid solution and enhance the hardness and so wear resistance. It can also lead to the precipitation hardening, like in presence of certain alloying elements under the controlled heat treatment condition, we can have certain kind of the precipitates which will offer us the desired set of the properties. Similarly, we can introduce certain kind of the dispersion hardening constituents, like in the matrix of the aluminum we can add tungsten carbide, chromium carbide at the surface layers. So the composition of the near surface layer is altered and we are having the desired constituents and desired properties at the surface in terms of the wear and friction behavior. Similarly, this change in chemical composition can also alter the stacking fault energy of surface layers. Just an example of that, what we can see here, like simple carbon steel which does not show much of the work hardening behavior. So if the surface layers are deposited in such a way that it is having the austenitic stainless steel or high manganese steel. So both these offer good work hardening behavior because of the low stacking fault energy. So despite of the high stacking fault energy of the simple carbon steel, if we deposit a layer of the low stacking fault energy material at the surface, it will result in the good wear and friction behavior as per our requirement. So the compositional modification can affect the wear and friction behavior in various ways, which includes like grain refinement, solid solution strengthening, precipitation hardening and dispersion hardening. It can also cause the transformation hardening, like in carburizing, where carbon content is increased and thereafter controlled heat treatment leads to the formation of the martensite. So it can also be in form of the transformation hardening and then changing the stacking fault energy by having a particular kind of the surface material at the surface. So these characteristics affect the wear resistance of the material. Why? Because whenever these kind of the hardenings and change in behavior will be taking place, this will be leading to the improvement in the hardness, surface energies and the work hardening tendency. So wear and friction behavior will be influenced because of variation in these three characteristics. So what we can do for changing the chemical composition, basically these are the thermal methods which are used. So surface composition can be modified using the thermal methods. There are two approaches. One, the component whose surface composition is to be modified will be exposed at a high temperature in the environment of which is rich in the required element, say it may be carbon or nitrogen or vanadium or anything else. So these will be diffusing into the surface. So diffusion is one approach. We are changing the surface chemistry based on the diffusion principle. Second is where surface layers. Second approach is what? Where surface layers are brought to the molten state. So surface layer will be brought to the molten state and then required elements which we want to introduce at the surface will be brought in. So developing either melting the substrate layer and then introducing the required elements like tungsten carbide or introducing the chromium or molybdenum at the surface, or we can just simply deposit without melting the substrate material. We can deposit one layer of the required material by development of the coating. So both these will be involving, both these approaches involve basically the melting or the fusion of the surface. So, developing a layer of the material having the desired composition to realize the properties which are required to regulate the friction and behavior of the material. Further aspects related with the approaches I will talk in the next presentation. Now, I will summarize this presentation. In this presentation, basically I have talked that there are 5 important surface characteristics that matter for the wear and friction behavior of the material. These are the surface energy, chemical composition, microstructure, surface hardness and the surface roughness. In this presentation, basically I have elaborated the surface energy and chemical composition and the way by which it can affect the wear and friction behavior of the material. Thank you for your attention.